So we're going to talk now about cell potentials, the voltage involved when there's a flow of electrons. I just want to remind you that when we talk about voltaic or galvanic cells versus electrolysis, if you remember the example I gave you, where the voltaic or galvanic cells are where it's self-producing for energy, the electrolysis is where it's getting energy from another source. So your cell phone battery is what I used in class, where when it's in your phone and it's not plugged in, that battery is behaving like a voltaic or galvanic cell. And when your phone is plugged into the charger, that is when it's getting energy from another source to be recharged. So with the voltaic cells or galvanic cells, we talked about the anode, which is the oxidized or oxidation side, and the cathode, which is the reduction side, where we have a metal in an aqueous solution separated by either a salt bridge or porous barrier. And we have the metal here with an aqueous solution. So what's happening on the anode side or oxidation side, and again, I remember it because oxidation is loss and it's negative and it's the anode. An anode reminds me of anion, which is negative. So it's just kind of a way I remember it. So electrons are lost from the solid metal, leaving the ions, the metal ions in solution, while the electrons travel through the voltmeter. And the voltmeter is what measures the amount of electrons flowing through. And they go over to the cathode, and the cathode is this wire is attached to the cathode, which also is a metal, and it is positively charged because the electrons are being added to this whole thing. So the electrons go into this metal, and then the ions that are in solution grab onto these electrons and precipitate out back as a solid. Again, in theory, theoretically, if all of the ions were in solution from the oxidation and all of the anions were back to the metal, if we let this go on for an infinite amount of time, eventually the anode would completely go away and the cathode would be doubled in size. All right. The salt bridge is what allows this electron flow to not stop. So what that means is there's going to be anions and cations either in the salt bridge or the porous barrier, allowing anions and cations to, kind of go through it to keep the flow of electrons moving. There constantly has to be anions, cations, and full, solids and ionic compounds in solution to keep this flow going. Now, when we talk about EMF, electromotive force, you guys all know that the reverse of this waterfall, meaning instead of the waterfall flowing down, the reverse of that, all the water here flowing up, that's not going to happen. It's not going to happen because it's not spontaneous. We can hit rewind on a videotape, but the reality is the water flowing upwards is not going to happen. It only is spontaneous flowing downwards. In the same way, electrons only spontaneously flow from the anode to the cathode. Cathode to anode, not spontaneous, not going to happen. This waterfall is not going to go up the hill. We also know that at the peak here, there's the highest potential energy and the lowest potential energy when it hits the water. And that kinetic to potential energy shifts as the water falls over the waterfall. Why does this matter? Well, it matters because the difference between the anode and the cathode in the cell is the EMF. We also call it the cell potential, electromotive force, EMF, or cell potential. So fancy E, subscript cell, there should be a knot here, a little knot right there. I don't know why it's not there, but there should be. So we can measure it in volts, and this will be given to you on your useful information sheet for your final. But 1 volt is equal to 1 joule per degree Celsius. And reduction potentials, meaning what's going on, are on a table. You don't have to memorize this table. You don't have to know this table. The values will be given to you, but you do need to know how to use them, and you do need to understand what they mean. So if I were talking about, for example, the first one, and we talked about this again a little bit in class today. If I were to talk about iron in its free state and adding to it 2 electrons, I'm going to get 2 fluoride ions. So that is a gain of electrons, therefore it is reduced, and we get a positive value. If the reverse of this happened, where I have 2 fluoride ions and they were giving off 2 electrons to get back to F2, this value would be flipped for the sign. So it would be negative 287. If for some reason we would have to multiply by a multiplier to make sure everything works, this is not like enthalpy or entropy. We do not multiply this E naught reduction value. Do not multiply it. Even though you have to do the multiplier here for balancing, it is not done here. So there are kind of 2 ways we can look at this. The first way we can look at this is manipulating the equations, which you will see in the supplementary video that I upload, which I did not do, but you'll see in the supplementary video that I upload. Or you can simply just use this equation. The cell potential overall is equal to the cathode minus the anode. Now, if we go back, this is the flow of electrons clockwise. So the electrons are going from left to right. You can kind of think about the cathode as products and kind of think about the anode as reactants. Much in the same way, we are back to products minus reactants, because the cell potential, this whole thing here is important. The cell potential is based on the potential energy per unit of charge. It is an inverse property. So if we have this particular example, we have a zinc anode in a zinc nitrate solution, and it's zinc 2 nitrate. We have hydrogen gas in a nitric acid solution where hydrogen is being bubbled in, and the nitrate anions are kind of dealing with the salt bridge. Excuse me. Then what we see is that zinc is being put into solution as an anion as the electrons leave the solid zinc to flow through. And when they flow through, these hydrogen ions are going to come up into the hydrogen gas and reform as H2 gas, taking on the electrons that have flew from the zinc to the hydrogen ions. Meanwhile, the nitrate anion that is left behind is going to be attracted to the sodium nitrate, the sodium of the sodium nitrate that's in the salt bridge. Those are going to be attracted to each other. And likewise, the zinc 2 ions are going to be attracted to the nitrate ions in the salt bridge. This salt bridge is what keeps this process going and circling. So We know that because zinc loses 2 electrons, it is oxidized. We know that hydrogen ion gains 2 electrons to form hydrogen gas, so it is reduced. The numbers for this have already been worked out and are on a chart and will be given to you. So there is a typo here, by the way. This should be E, not OX, not E, not RED. So the oxidation is negative 0.76 volts, and the reduction potential is positive 0.34 volts. Now, the trick is, for electron flow to occur, we know the overall cell potential must be a positive value. So if we use this equation where E naught cell equals cathode minus anode, remember, that's a typo right there. Sorry, can't change it while I'm in recording mode. It's going to be plus 0.34 volts minus a negative 0.76, giving us a positive 1.10 volts for the cell potential. We have a positive number, so we know we're good to go. So this reaction right here gives us a positive cell potential of 1.10 volts. Now, if you relate this to your everyday life, you're going to remember that batteries are in voltages, light bulbs are in voltages, or watts, which can be converted. Everything that has to do with light or power in some way, shape, or form can be converted between volts and any other unit. Now, the oxidizing and reducing agents that occur, the strongest oxidizers have the most positive reduction potentials. The strongest reducers have the most negative reduction potentials. Reduction means gain of electrons. Why does this matter? Because it has to do in which way the reaction is going. Is it the forward or the reverse reaction? Okay, so this is where I'm going to end the electrochemistry mini lecture. I am also going to post a supplementary lecture to this, and when I post the announcement about it being uploaded, I will go ahead and I will tell you, remember I said this is the video that's like super, super long. It's like an hour and a half or something. I will give you a stopping point for that particular video, okay? If you have any questions, let me know. I will have limited access to email over the holiday break. Enjoy your Thanksgiving. Gobble, gobble.